Hello everyone. In this clip, we will learn how to design an AC to DC circuit, and we will use a four-way rectifier circuit. This is a two diodes type. Below is our design scope. We want to converting an AC voltage source is from US. We use 120 volt RMS and the frequency is 60 Hz AC. We're converting that to a DC voltage. So our goal is to make a DC voltage that's slightly above the 14 volt and the load current is 0.5 amp. We will use a four-way rectifier circuit design. The reason that we want to use the 14 volt DC output is later on we can use this for a linear regulator. It's an LM7812 12 volt output from Texas Instruments. Below is the first circuit. We will construct it in symmetric SPI model. This is a voltage source on the left side that we have a 120 volt AC source. We apply it to a transformer. This transformer is a center tap transformer. It's able to handle the low frequency at 60 Hz and the source is 120 volt. On your secondary side, we have two diodes, one and 5811, and I will putting a load, a resistor load, roughly around 0.5 amp equivalent. So this is a type of four-way rectifier. It is not really smoothing out to become a DC voltage source yet. So when we're getting into a detail of the symmetrics, I will explain it more detail of the turn ratio and everything else. And we use the 1N5811. It has a forward drop of almost 0.9 volt. It has a 6 amp capable for the diode, and the reverse voltage is 150 volt. And on our second schematic, this is a more detailed. You will smoothing out your rectifier waveform and making it almost like a DC waveform. So in this circuit, I will explain it, how we design a capacitor that we can control the ripple going through it. So let's go to the symmetrics model and we'll learn how the waveform look like and how we can apply for the capacitor, adjusting it to make it like a DC voltage source. So this is our first four-way rectifier. So we will run a simulation on this one. The transformer has a turn ratio of 10:1. If the primary 10 turns, the secondary will be 1 turn. So we simplify it. So if you have a peak voltage of 120 volt, you multiply by 1.414, you will get roughly 170 volt peak voltage. So by dividing it down by 10 times, your secondary side right here would be about 17 volt. Then if you drop about 1 volt across the diode, the output will be 17 volt minus for 1 volt. We will get a peak voltage of 16 volt at the output. So let me do the simulation and you will see it more clear. So in the result, we will see that the primary waveform is a sinusoidal waveform, a 60 Hz frequency. And on the secondary side, we see a four-way rectifier, flipping everything into a positive side. And you see that at the output, we hit around 16 volt, about 16 volt at the peak level. So pretty much matched with what we calculated. So this is our first step. So this waveform is not quite a DC waveform yet, so we needing to putting in a capacitor to smoothing out the waveform and converting it into almost like a real DC waveform. So let's move on to the next step. So this is our complete circuit that we're converting from an AC to a DC source, and we're putting in a tantalum cap or aluminum type of capacitor here. So the first step that you already understand that we're converting it and we're getting a rectifier waveform here around 16 volt peak. So now our next step is that how do we selecting the capacitor here to getting the voltage above the 14 volt and control the ripple voltage across the output. So the basic equation is the IC is equal C times for dV divided by dt. dV is the ripple output voltage and dt is related to the frequency. It is 1 over f. The frequency in this case is twice your primary frequency since you're converting it to become a full wave. So if a 60 Hz, our frequency on the secondary side will be 120 Hz. The IC, which is the load current, so we will use it 0.5 amp load. So if we want to design a 1 volt peak to peak ripple, so you are the one who pick it. So I will pick 1 volt in this case. So my equation will become C equal IC times for dt divided by dV. And remember, this is more realistic. We will have a square root of 2, so it's similar like an RMS type of voltage in this equation. So finally, I will have an equation of capacitor will be equal to the load current times for 0.707. I'm converting the 1.414, bring it to the top, and the whole thing divided by the ripple voltage, which is 1 volt, multiply for 2 and then the frequency f. So with that I will get 2900 microfarad. So in my model I using two 1500 microfarad cap. So my estimate is that the minimum output will be 16 volt, which is the max peak, minus for the ripple voltage of 1 volt. So my minimum voltage will be 15 volt, which is slightly above the 14 volt that I can apply it to the LM7812 for the linear regulator output. So let's run a simulation and see how the result come out and see if it match with our calculation. So the top green curve is the primary AC 120 volt RMS and a 60 Hz frequency. And on my output voltage now, you can see that we have a ripple voltage of around between from 14 roughly, let me see right here, I have the bottom one is roughly around 14.7 volt, and then on my max peak right here I got around 15.9 volt. So the total ripple is around 1.16 volt. If you can see on my right side here, total ripple is almost 1.2 volt, very close to what we expected. And it is the bottom part. It is 14.7 volt above the 14 volt that we want to design. So this is my secondary circuit, which is important that we know how to select the capacitor for the design. And as you can see that inside the tantalum cap there is an internal resistance we call ESR. So this ESR contributed to the ripple voltage. That's why you're seeing it a little bit higher than we expected when we calculated. So this is the end of the design circuit for a simple full-wave rectifier circuit, and I hope you can learn something from this video clip. I will see you on the next one. Thank you.